What's up, people? Welcome. First of all, I'd like to apologize for coming late. There was some tech issues. My internet was not stable. That's why I couldn't come live. Anyways, I'm back now. I'm here now. I hope you guys can see me and hear me and everything. What's up, people? Hi, Nilay. Hi, Tamashri. What's up? Hi, Arjun. What is up, people? Hi, Riza. What's up? Hi, Zen. Yo, hi Satvika, what's up? Welcome, people, welcome. Sorry for coming late again. I hope, thank you for waiting up. Thank you for, thank you for deciding to spend your time with me. So, very warm welcome. My name is Anoop. This is Vedantu's 9th and 10th English channel where we will be talking about magnetic effect of electric current in one shot. So, as you guys know, we have completed the entire chapter of magnetic effect of electric current. As you might already know that you only have till Fleming's right hand rule. What to say? The working of generators have been removed from your syllabus. So since that is not a part of the syllabus, what we're going to do in today's session is basically we're going to look into the entire chapter all at once, from the very first till the last. That is from Oersted's experiment till Fleming's right hand rule. We're going to look into all of it at once. We're going to quickly brush through the concepts. So for all those who have not attended the previous session, this is going to be super helpful for you guys, because we'll be doing the entire chapter and we'll also be doing quizzes at the end of the session as well. So make sure you stay till the end, make sure you attempt the quizzes also, and make sure you make notes, write down all the important points, whichever you feel like, things that you might end up forgetting, write that down as well. And so that it'll help you with your board exam preparation, with your term 2 preparations. All right, so shall we start with today's session, people? Can I get a yeah in the chat box if you guys are all ready for the session? I'm good, Adi. Thank you for asking, buddy. I am negative, people, so I am COVID negative now. I was positive, but I'm negative now. Today was my test. I took that Fine, you call that. No, what is that? It's a home kit that you get. So when it's basically, it's not RT-PCR per se. It is basically a rapid test, but it turned out to be negative. So I'm negative now. Thank you for asking. Thank you for caring, people. Hi Nipanji, arey, what's up Nipan? What's up? Hi Tamara, what's up? Welcome. All right. So people, without wasting much time, we'll get into the topic. Now, once again, for all those who want to take part in the quiz, whoever's watching this session, who is not watching it live, because I'm pretty sure a lot of you guys do not watch it live. So whoever is watching the recording of this session right now, please go to the link in the description in order to take part in the quiz that is there at the end of the session. So you guys can take the quiz whenever you want. That is the whole chapter of magnetic effect of electric current. You can take the quiz over there as well. All right, so people, with that said, let's go on to the working of basically what we're going to do is basically do the entire chapter. Here they've given us DC motor. We have already done the DC motor part. So what we're going to do is, guys, we'll do the entire chapter of magnetic effect of electric current. So everyone listen carefully. It's going to be a long lecture. It's going to be a lot of me talking and you listening, because again, this is the one shot series. As you might know, in one shot series, we basically cover the entire chapter in simple words. So make sure you write down all the important points as I say it, so that you guys can refer to that when your exams come up, so that you don't have to go through the entire textbook and struggle while when you're nearing the examinations. That's why, right? Okay, so the first thing that we learned in this chapter, people, was about Oersted's experiment. So there was this guy called as Hans Christian Oersted who accidentally found out about the magnetic effect of electric current. So basically what happened was that he had a simple circuit which he had kept on a table, and he had a compass, the directional compass. Now, as you might already know, the compass that is there is basically is magnetic in nature. The needle of the compass is magnetic in nature. So what happened was that because when current is flowing through a conductor, there's a magnetic field created. Again, at that point of time, we had no idea about it. Oersted also had no idea about it. But accidentally, he saw that the needle inside the compass started deflecting, and that is how the discovery of electromagnetism or magnetic effect of electric current came into existence. And since then, we've been doing a lot of experiments based on it. Now, there are two terminologies that is very much much synonymous with magnetic effect. One is the the magnetic field, and the other is magnetic field of lines, or you can say the magnetic lines, or either magnetic lines of force or magnetic field lines. So magnetic field is nothing but the region around a magnet. So if I take a certain magnet, you see that there is a certain region around the magnet where the magnetic field, or you can say that the magnetic force is experienced. Now, if you keep any magnetic material outside this field, there'll be no change whatsoever. You'll not see any attraction, you'll not see any pattern, nothing of that sort. So that region around the magnet, that is called as a magnetic field. The region around the magnet where you can experience the magnetic force, that is called as the magnetic field. Magnetic lines of force are nothing but, guys, when you take when you look at these, the arrangement of these iron filings or iron pieces, you can see that these iron filings or iron shavings are basically arranging themselves in a particular format. It's not an irregular structure. There's a proper, you can say that there's a pattern to the chaos, right? So it looks chaotic, but then it's actually not. If you look very carefully, you can see there is a certain pattern to it. So this is what is called as a magnetic lines of force or magnetic field lines. Basically, it talks about the direction of the magnetic force acting around this magnet, and it also gives you an idea of in what way the magnetic force is acting around the bar magnet. So in a bar magnet, please remember, guys, you have a north and a south pole. So always remember that the magnetic lines of force or the magnetic field lines are originating from the north pole and they are ending in the south pole. So they originate from the north pole and they end up in the south pole. But inside the magnet, however, the magnetic field lines are going from south to north. So this is how the pattern basically looks like. So it's actually a continuous loop. It's not some irregular half structure. It's a continuous loop where the magnetic field lines are going from south to north as well as from north to south. Outside the magnet, north to south. Inside the magnet, it's going from south to north as well. Now there are certain properties of these magnetic lines of force. Like if you look at it over here, you can see that there are few places where the magnetic lines of force are very close to each other. Wherever the magnetic field lines are close to each other, there you can see that the magnetic field is very, very strong. So especially near the poles, be it south or the north pole, around a bar magnet, it's very strong there. That is why you see that they're very, very close to each other. So because they're very compact, they're very close to each other, you can come to the conclusion that the magnetic lines or magnetic field is far more stronger in the north and the south pole. But if you go towards the middle, you can see that there's a lot of gaps in between, and wherever there's a lot of wherever there's a lot of gaps in between, or wherever they're spread apart, there the magnetic field is comparatively weaker. So if you take a bar magnet, the magnetic field is the strongest near the poles, and you can say that it's weakest near the mid region, as you see in this particular diagram. And apart from that, I told you already, people, all magnetic field lines, especially when you talk about a bar magnet, or if you talk about a horseshoe magnet, or magnets in general, these start from the north pole and end up in the south pole, and inside the magnet they are going from south to north. All right, so these are some of the properties of the magnetic lines of force, right? Just by looking at the diagram, you can easily make that out. Now, if in case, people, let's say that you don't have iron filings and you still want to find out the magnetic lines of force around a bar magnet, then what you can do is you can take a compass. So what you do is that you place the compass in different location, and wherever the north pole of the compass is basically pointing towards, you see that that is the direction in which the magnetic lines of force are going away from. So you can see there's a pattern to this also. So you can actually find out the direction of the magnetic field using this compass as well, by placing it at different positions. Now, apart from that, if you look at any of these diagrams, you see that none of the diagrams are actually intersecting each other. It's not, it's like they're all very obedient. It's like ants. In an ant colony, it's like they're always going in a straight line. You don't see ants crossing each other and fighting against each other at all. So it's very similar to that. Here also the magnetic field lines will never intersect each other. There are two reasons for that. One is because if you want to find out the direction, for example, let's say that I want to find out the direction of a magnetic field line, at this position. So if I want to find out the position of this magnetic field line or the direction of the magnetic field line, all I have to do is draw a tangent. I'm pretty sure you guys know what a tangent is. You've studied that in circles. So tangent is nothing but, if I take a circle, it's nothing but a straight line that is just touching the circumference, right? So if I draw a tangent, I can actually find out the direction of the magnetic field lines. So here also you can see that, see, in a particular point, you can't have two different directions. So here you see this, there's one direction this way, there's one this way, which is never possible. Also, if you place a compass here, let's say I place a directional compass, you know, the north and the south pole wala compass, right? If you place that compass over there, you have two north pole. Now that is the thing, you cannot have two separate north poles. You can't have a compass pointing in two different north poles. You can't do that. That is not physically possible. And because of this reason, people, no two magnetic field lines will ever intersect each other. All right, is that clear, people? Understood? I hope you guys, please hold on with your doubts. I'll try to clear it up towards the end as well, because right now, you know, I want to finish off the topic. First of all, you know, let's finish off the topic very quickly, and then whatever doubts you have, put it down. I'll try to clear it in the meantime. All right. So why magnetic monopoles don't exist? Because again, you know, whichever magnet it is, you cannot have one pole basically, because if you look at the magnetic field lines also, it's a continuous loop. It's not like it's starting from one point and it's going on forever. It's a continuous loop. So you cannot have you cannot have single poles. In nature, it is not possible for a single pole to exist. It's always bipolar, or you can say that you should have a north and a south pole. You can't have just north pole alone or just south pole alone. Even in the, see, if we do talk about diagrams also, for example, if we talk about motor diagrams also, what we do is that we write one side is north pole, one side is south pole, but that does not mean that you have a magnet which has only north pole. It is basically one single magnet. It is represented that way. That's why, all right. But you cannot have one single pole in nature. All right, it's always going to be bipolar, always, no matter how small the magnet is. Let's say I take a big magnet and I divide it into half. It doesn't matter. So this is the north pole, this is the south pole. Once I divide in half, this will become north and south, this side will become south pole, and the other part will become south and north. So whatever it is, no matter if I divide this again in half, it will still have a north and a south pole. All right, I hope it's clear there. Anyways, moving on, people, moving on. Apart from this, people, we also learned about the magnetic field lines around current carrying conductors. We talked about 3 different current carrying conductors. We talked about straight line current carrying conductor, circular loop current carrying conductor, and a solenoid as well. Now, in a straight current carrying conductor, the magnetic field is very simple, very straightforward. If you have a straight current carrying conductor, the magnetic field are basically concentric circles. You have one circle after another, one circle after another. This is what the magnetic field lines look like when you talk about a straight current carrying conductor. Now, if you want to find out the direction of the magnetic field here, all you have to do is use the right hand thumb rule. Basically, this was actually made up by Maxwell. So according to Maxwell's right hand thumb rule, what he said was that if I have a straight current carrying conductor, all I have to do is this: grab hold of the conductor such a way that the thumb represents or shows the direction of current. Now here you see that the direction of current is going downwards. So current is going downwards, which is indicated by my thumb. The rest of the fingers which are enveloping the conductor, that is showing the direction of the magnetic field. So which you can see that the magnetic fields are basically going like this. So you have to look at the direction of these nails. So wherever your nails are pointing towards, that is the direction of the magnetic field as well. So this would be the direction of the magnetic field. All right. So this is how you find out the direction of a magnetic field around a straight current carrying conductor. So if you want the theory, people, this is what it is. You can make a note of it, take a screenshot if you want to. Anyways, I'll be putting up the notes of the session at the end of this session, but nonetheless, you can take a screenshot just for your reference. So here you can see that the current is going in the upward direction. So if you look at the nails, you see that they're going in anti-clockwise direction, right? So this is how it is going to be. So thumb shows the direction of current and the curled up fingers shows the direction of the magnetic field. So that's what the right and thumb rule. It's basically Maxwell's right and thumb rule. The second thing that we learned was basically how the magnetic field lines look, around a circular loop. Now, in a circular loop, people please understand that in a circular loop also it's very similar to that of a straight current carrying conductor. Why? Because a circular loop can be said that it is made from several straight conductors. So I can make a circle out of several straight conductors once I place it in a certain pattern. So you can see this. So this pattern basically almost is very similar to that of a circular loop. So in a circular loop, you saw that how the magnetic field is concentric circles, right? So here also it's going to be concentric circles, but the only difference is that as you go towards the middle, so this is the top view when you see from the top, right? So as you go to the middle, you see that the magnetic field lines are getting straighter and straighter. So near the center, it's almost going to be a straight line. The reason is because the magnetic field is getting uniform there. Because if you just look at this diagram, each and every point has its own magnetic field. So there's what do you say? If you go towards the middle, the distance from the middle is almost equidistant, right? It's almost equidistant from here to here, from here, because it's a circle. It's a circle. So from the center, the distance is almost the same. And because it's almost the same, what happens is that the amount of force acting over there is constant from all the sides, or uniform from all the sides. And because it's uniform, it's almost going to be a straight line as we go towards the center. But there's one more thing you need to know about a circular loop, and that is called as a clock phase rule. Very important that you remember this, people. What does this clock phase rule is nothing but, according to the clock phase rule, whatever side you're facing, if the current is flowing in anti-clockwise direction, then you can say that that is basically the north pole. Since again, this is also behaving like a magnet, and any magnet has a north and a south pole, as I have mentioned before. You cannot have one single pole. So since current is flowing in anti-clockwise direction and you're facing it, that would be the north pole. And if a current is going in clockwise direction, as you see over here, you can say that the current that side would be the south pole. So if one side is north pole, for example, for you, if current is going in clockwise direction, for me it will be in anti-clockwise direction. If for you current is going in anti-clockwise direction, then for me current is going in clockwise direction. So one side is north, one side is south. All right. So if you take a circular loop, one side is north, one side is the south pole. Talking about a solenoid, people, solenoid is by far the most easiest of them all, because the magnetic field around a solenoid is very similar to that of a bar magnet. It's absolutely similar to that. So it's one of the most easiest to remember. It's very similar to that. So you have magnetic field lines starting from north pole, ending up in the south pole, exactly like how it happens in a bar magnet. But the only difference is that here you can actually see the magnetic field lines inside the magnet also. So if you talk about a bar magnet, we don't show that as much, but here you can see, because it's hollow in the center, the magnetic field lines are passing through the center as well, and it's pretty strong in the center. Why? Because you can see that the magnetic field lines are very compact, they're very close to each other, so the magnetic field over there is very strong, and it's also uniform as well. And this is how you make electromagnets. So if you take a soft iron core, basically a soft iron core is nothing but iron with lower melting point. So if you place a soft iron core inside this solenoid, that can also get magnetized. So what will happen is that it will actually increase the strength of the magnetic field around the solenoid if you place a soft iron core, and it also gets magnetized as well. If it's a magnetic material, that can also gets magnetized. So this is how temporary magnets and all are basically made. All right. So this is what it looks like in a solenoid. And again, if current is going in clockwise direction, then that is the south pole. So if current is going in anti-clockwise direction, so you see this here, current is going in clockwise direction. This is the direction of current. So that means that is the south pole. The other side would be the north pole, because over there current is going in anti-clockwise direction. So if current is going in anti-clockwise direction, you can say that would be the north pole. So basically the clock phase rule, you have to use it over here as well. Apart from that, guys, talking about the factors affecting the strength of the magnetic field is one of the most easiest thing to remember. This is the only formula that you have in this chapter of magnetic effective electric current, and the best part is you don't even have numericals from it, but it's a very simple formula. You need to know the formula. You won't be asked any numericals, but you might be asked the theory part of it. So what are the factors affecting the strength of the magnetic field? One of the things is that the more number of turns that you have in a solenoid, the stronger the magnet, the stronger the magnetic field. The second is the stronger the current, more would be the magnetic field. And by inserting a soft iron core as well, you can actually increase the magnetic field around it, like I mentioned before. So here you see this, the number of turns are less. Here you have more number of turns, so the magnetic field will also be much more stronger. It will have a stronger magnetic force around it. If you increase the current also, that can also increase the magnetic field, and if you insert a soft iron core, that can also increase the magnetic field. Now the formula, people, as I mentioned before, the formula, it's not meant, it's mentioned later on, but I'll just write it down anyways. So the formula to find out the magnitude of force, that is the magnetic force, is basically F is equal to BIL, where B is the magnetic field, I is the current, and L is the length of the conductor. So we'll talk about that in the upcoming, like I told you, that is the only formula that you have. So please do remember it. So basically it says that force is directly proportional to the magnetic field, force is directly proportional to the current, and force is directly proportional to the length of the conductor as well. So you can write this as F is proportional to BIL. Now this, what happens is that here, to remove this proportionality sign, we introduce a constant called as K. So the formula becomes F is equal to K into BIL. But here, guys, K value is equal to 1, because if you take the SI unit of all of them, K value will be equal to 1. So you can say that F is equal to BIL. So this is the only formula that you have in this chapter. So please do remember it. Make sure you take a screenshot of this and remember it. You might have theories based on it, but there are no numericals. You'll have theories based on it. All right, moving on, guys. Now we also learned about something called as the Lorentz force. So this formula is basically from Lorentz force itself. So if we talk about what to say, if you take a current carrying conductor and place it in a magnetic field, you see that the conductor will experience a force. There's a force experienced by the conductor. This force is what is known as the Lorentz force. So what happens is that we know that when current is flowing through a conductor, there is a magnetic field created around it, or in other words, it behaves like a magnet. This magnet, you see that this is a permanent magnet. This is a horseshoe magnet, which means that it's a permanent magnet. It already has a magnetic field. So what happens is that there is an interaction between the magnetic field produced by the current flowing through the conductor and the magnetic field of this magnet. So because of this, what happens is that the conductor will experience a force, either an attractive force or a repulsive force. This can be found out by using Fleming's left hand rule. This is the the second hand rule that we're going to be doing. First is the Maxwell's right and thumb rule. Second one is Fleming's left hand rule. Very important, please do remember this. So according to Fleming's left hand rule, what he said was basically, if you extend your thumb, your index finger and middle finger such a way that they're all perpendicular to each other, what you notice is that the thumb shows the direction of the force on the conductor. So like I told you here, there is a force experienced by this conductor. So the direction of force is indicated by the thumb. The index finger shows the direction of the magnetic field, which is always going from north to south, and your middle finger shows the direction of current. So here you see this is, let's say that the current is flowing in this direction. You see this, so current is flowing in this direction. So your middle finger shows the direction of current, which is flowing in this direction. The magnetic field is going from north to south, so it's going in this direction. So your index finger shows the direction of the magnetic field. So if you look at the direction of force on the conductor, it's going upwards. So basically this conductor will experience a force in the upward direction. Very important to remember this, guys. The reason why this is so important is because you are going to be needing this when it comes to DC motors also. The whole concept of DC motor works on this principle. So super duper important. Now if you change the polarity of the magnet or the polarity of the cell, that can also impact the direction. For example, you see this here, the current direction is this way, but here what happens over here is that the conductor is moving towards the magnet. But when I change the polarity, you see this from this is the north pole, this is the south pole. So here they've changed the polarity of the magnet, so they basically change it from north to south. So when they change the polarity of the magnet, that can also impact the direction of the conductor. So here if you look at it, the direction of current is still this way, So current is flowing in this direction, which is shown by my middle finger. The magnetic field is going from north to south, and if you look at the force on the current carrying conductor, it will be basically towards you. So this is how you find out the directions over here. Very important. Please do remember this. If there's any confusion, I've already done this in detail in the previous sessions. Please go check that out. Now, talking about the direction of this magnetic field, guys, it depends on two factors. One is the direction of the magnetic field. Like I told you, if you change the polarity, that can impact the direction of the force on the conductor. And if you change the direction of current also. So if you change, let's say this, I'll make this as negative and this is the positive terminal. If I turn the battery around and change the polarity, that can also impact the direction of the magnetic field as well. So talking about the factors, guys, like I told you, the factors affecting the magnitude of this Lorentz force, this is called as Lorentz force. So if you talk about the factors affecting this Lorentz force, I think the spelling is Lorentz. Very similar to that. Lorentz force. Let's keep it simple. Let's keep it as S. So this is called as the Lorentz force. Basically, Lorentz was the one who found it. So talking about the factors affecting Lorentz force, the magnitude of it is in current, more would be the force experienced by the conductor, more is the magnetic field. So if I replace that magnet with a stronger permanent magnet, that can also impact the force on the current carrying conductor. And finally, guys, the length of the conductor is also a factor. So this is how we came up with the formula. I've already written down the formula. This is basically the formula to calculate the magnitude of Lorentz force. So if you want to calculate the magnitude of the Lorentz force, this is basically the formula to calculate that. So the formula is F is equal to BIL. So please do remember this, people. So that's how you came up with the formula. Here K is a constant, so it'll be equal to 1 if it is the SI unit. So the formula becomes F is equal to BIL, where F is the Lorentz force. Oh, my spelling was correct. All right. Anyways, moving on, people. Moving on. Talking about sometimes you when you're over smart, you doubt even the smallest things. First of all, all these texting has spoiled my spellings. Honestly, all this texting, like when I'm writing a spelling, my mind is like automatically it'll get corrected. Because when you're texting someone or when you're typing on laptop, you have this auto correct option, right? If you type a wrong spelling also, it'll automatically correct you. So in real life also, I'm expecting someone to correct my spellings automatically. Getting it? So it's basically, what do you call? It's like brains wired in a different manner. Anyways, moving on, people. So one of the most easiest way to remember, I forgot to tell you this, an easiest way to remember, the Fleming's left-hand rule is basically, people, you can remember it as father, mother, child, or you can remember it as FBI. Whatever floats your boat, please remember it that way, FBI or father, mother, child, where F is the force, mother is nothing but the magnetic field, and the child is nothing but the direction of current. So you can remember it that way, or you can remember it as FBI. Whatever is easy for you to understand, remember that way. Talking about the DC motor, on the other hand, people, DC motor, where is a very important topic, 5-mark question if it is asked, direct 5-mark question. So this is a very, very important one. So DC motor, there are 3 things you need to know. One is the working principle, the construction, and the working of the motor itself. So working principle is very simple. It works on Lorentz force. It works on the fact that if a current carrying conductor is placed in a magnetic field, it will experience a force. That is the basic funda behind the working of a DC motor. So this is the construction of it. Very important. I'll tell you the parts very quickly. So this is the external circuit that you have, where you have the battery and the wires, which is then connected to the carbon brushes. So carbon brush, in the sense, it's made up of graphite. Then you have the split ring, which basically is divided into 2. The split ring in return is connected to a armature coil. So this is the armature coil A, B, C, and D. And you can see that the split ring and the armature coil is free to rotate, right? They are free to rotate about the axis. Now, at the end of this split ring, you will have an axle, and this axle basically rotates as the armature coil rotates. You also have a magnet, which is which is shown by the north and the south pole. So here, if you look at it very carefully, people, there are few parts in this DC motor which can actually rotate. So those are called as rotors, or which is free to move about an axis. Those are called as rotors. Whichever is stationary, they are called as stators. So here, magnet is a stationary object, armature coil is a rotor, axle is a rotor, split ring is a rotor. brushes are stators, electric circuit are stators. So you have 3 stators and 3 rotors in the case of DC motors. Any part that does not move or does not spin, those are stators. Anything that is free to rotate, those are called as rotors. Very important. The armature coil is the one that is experiencing the force. You see this? This is the current carrying conductor which is placed in a magnetic field. So the current carrying conductor, that is the armature coil, will experience a force, and thus it will start to rotate. And as that rotates, the split ring will also rotate, and as the split ring rotates, the axle will also rotate. So this is how you see this. This is the axle which is connected at the end of the split ring. So as all of these rotate, the axle will also rotate, and at the end of the axle, you would basically be connecting a fan or any other device that you want to work, and it will work according to that. Okay, people. So this is if you talk about the working principle, it's actually quite simple. I'll just quickly explain that as well. All right, talking about the so what happens is this, people. So you see if you look at it over here, see that the current is flowing from the positive terminal, goes through the carbon brush. I'll call it as B1. I'll call this as B2. Through the carbon brush, it will enter into the split ring, which is R1. Through the split ring, it will enter into the armature coil. Once it enters into the armature coil, now pay attention, guys, pay attention. Current is going from A to B. Current is going from A to B. I am going to use my Fleming's left hand rule here. So listen carefully. The direction of current is shown by my middle finger. So current is going from A to B. It's going in this direction. Magnetic field is going from left to right. See, this magnetic field always goes from north to south. So this is the direction of magnetic field, which is shown by my index finger. So my index finger shows the direction of the magnetic field. Current is going from south to north. So what is the direction of the force on this conductor? It will be downwards. So AB will experience, the armature coil AB will experience a force downwards. But if you look at BC, see, here if you look at it, the direction of current and the direction of magnetic field, they are both parallel to each other. Since they are parallel to each other, BC and AD will not experience any force. All right, since they are parallel to each other, there'll not be any force. There'll be no force acting on them because they are both parallel to each other. All right. See, maximum force is when they are perpendicular to each other. When they're parallel to each other, it's because the angle is 0. All right. Because if you look at the formula, also it's actually F into BIL sine theta. So since sine 0 is 0, the whole value becomes 0. All right. But yeah, we'll talk about that later. All right. You'll study about that in your higher grades. Moving to CD, people. If you look at the direction of CD, the current is flowing downwards, so which is shown by my middle finger. Current is going towards me. My the magnetic field is still going from left to right. So if you look at the direction of the force on the conductor, it is going upwards now. So CD will experience a force in the upward direction. BA or AB will experience a force in the downward direction. Because of which, what happens is that the armature coil will start to rotate. Now, what happens is that once it reaches halfway, so this is A now, this is B, this is C, and this is D. So basically it's now like this. All right, it's halfway through. So once it reaches halfway through, people, I'll just I think I showed this in the previous session also, but I'm gonna show it anyways. Yeah, this is the most amazing explanation that you'll ever see. So this is A, this is B, C, and D. Listen carefully. So what happens is that you can see the Amazon symbol. No. So what happens is it will experience a force. So this AB will go downwards, CD will go upwards. Now, once it reaches halfway, now please remember that there's a split ring. Now, the thing with split ring is that once it reaches halfway, current gets cut out because there's a disconnection there. So what happens is that this is how the split ring is going to be. So there's going to be a disconnection between the brushes. But since it already has some momentum, it will complete half a rotation. It will basically fall to the other side. It will complete half a rotation. So once it completes half a rotation, what will happen is that the direction of current will change. Because if you look at the armature coil now, here, the one that is connected to R, so what in place of R1, you have R2 right now. And if you look at the direction of current, it's DCBA. So direction of current has now changed to B1. The brush one is exactly the same. Now it's R2, DCBA. Then it goes to R1. Then carbon brush to number 2, and then it goes back into the the negative terminal. So the direction of current is changing. So once again, if you look at the direction of current, again CD will experience a force in the downward direction, because if you look at the current is going in basically current is going in this direction. Magnetic field is still the same. So magnetic field is still the same. So if you look at the direction of the force on the conductor, it will be downwards. AB on the other hand will experience a force in the upward direction, and this will continue to happen over and over and over and over again until the current is flowing through the circuit. All right. So once again, people, for all those who are confused about this one, see guys, the actual formula is F is equal to BIL sine theta. All right. This is the actual formula. Now, if you look at you guys already know what sine is, right? BIL sine theta is the actual formula. So if you look at BC and the magnetic field, they are both parallel to each other. So if they are parallel to each other, what is the angle between them? Angle between them is 0. Now, what is sine 0? Sine 0 is nothing but 0. So the whole value, because the force acting on them, will be 0. But if it is perpendicular to each other, then it will be maximum. So force, if the magnetic field, like in this case, you see this is the direction of current, and magnetic field is this way. So they're perpendicular to each other. When they're perpendicular to each other, sine 90 is 1. So it will be maximum. So this is basically the funda behind it, people. But we don't talk about this because you are meant to study about this in your higher grades. But this is just for your understanding. If you want to remember it, you can remember it. But yeah, it is still for your understanding. All right. So you can see the carbon brush, guys. You can see the carbon brush. Once it reaches halfway, current stops flowing. That's why you see that it becomes grayish in color, which means that the current is not flowing. But because it already has some momentum, it will complete the circuit. So every half rotation, the current's direction changes. Half a rotation, current will change. Full rotation will come back to its. So this will be A, B, C, D again. But half a rotation when you have, it will be D, C, B, A. So half a rotation, the direction of current would change, accordingly. All right, people. So that is about your DC motor. I hope it's clear. Talking about the factors affecting DC motor, because obviously you use DC motors in industries and all, and over there you can't just use a battery. You have a lot of things that you need to consider in the case of DC motors over there, because you need to produce a lot more power, a lot more energy. So in that case, there are a few ways to tamper around with it. One is by increasing the strength of the magnetic field. The more the strength of the magnetic field, the more would be the force on the current carrying conductor. Second is the current in the coil. More is the current, more would be the force on the current carrying conductor. And finally, guys, basically the RPM would be more. It will experience more force, which means that it will rotate faster. And finally, the number of turns. The more the number of turns, especially if you look at all these commercial motors, people, you'll have lots of copper wires which are wound around this inside this motor. If you open the case, right, you'll have a lot of these copper wires. So more the copper wire, more the number of turns, basically more would be the force acting on it. So that is another factor that it depends on. Finally, people, we also learned about electromagnetic induction as well. What is electromagnetic induction? Just a quick explanation on that. So electromagnetic induction is nothing but basically when you have a moving magnetic field or a changing magnetic field, and you bring that near a current carrying conductor. Again, imagine I have a conductor and it's not connected to any battery, any potential difference, any voltage source. What it's connected to is simply a galvanometer. A galvanometer is a device that measures the current. All right, I have a simple device that measures the current and nothing else. Now, if I take a bar magnet and I bring it closer to this solenoid, which is not connected to a battery or anything of that sort, you see that the galvanometer still has some deflection on it, and the direction of the deflection will also be changing when I move the conductor, when I move this magnet towards and away. So what is happening is that because of this movement of the magnet, the magnetic field is changing, because as you move the magnetic field also will change. Because of the changing magnetic field, there is a current induced, there's a voltage induced, there's a potential difference induced in this conductor. Because of that potential difference being induced, current starts to flow. But it's only for a split second. You need to have a continuous changing magnetic field. As soon as the magnet stops, the current produced would also stop. I've explained this in detail in the last session. It was an amazing one. You can check it out. I have talked about this. So today is actually 4th of February. So 3rd Feb, that is yesterday at 3 p.m. I done this exact session. I had done this in detail. I hope that you guys were there and you guys were able to you're able to understand this. But anyways, whoever is confused or whoever is still kind of skeptical about this or still has this confusion, so this is what happens, people. So when you bring a bar magnet closer, you see these are the magnetic field lines. So as you bring this magnetic field, or as you change this magnetic field, as you move this magnetic field, when it comes to the conductor, what is happening is that the magnetic field is getting cut. It is getting intercepted by this the current carrying conductor. Because of that interception, what happens is that there is a current induced, or there's a voltage induced in this circuit, and that is why the galvanometer starts to deflect. Now if you look at the direction of the deflection, that also changes with the direction of the magnetic field. Now in order to find this out, we have your Fleming's right hand rule here. If you want to find out the direction, this is what you have to do. So basically, according to Fleming's right hand rule, people, you have your thumb, index finger, middle finger, just like how you have your left hand rule, but the only thing is that here you're going to be using your right hand. So all of them perpendicular to each other, all of them perpendicular, all of them at 90 degrees to each other. So what happens is that your thumb shows the direction of the force on the current carrying conductor, or not the force, sorry, you can say that it's the thrust or the motion or the direction at which the magnetic field is moving, or the magnet of the conductor is moving. So either you keep the magnet and move the conductor, or you keep the conductor constant and you move the magnet. So that direction is shown by your thumb, which is basically the motion or the thrust. Your index finger shows the direction of the magnetic field, and your middle finger shows the direction of the induced current. The direction of the induced current is shown by my middle finger. So you can say, I remember it this way. You can use a different analogy if you want to, but I remember it as FBI. So F is nothing but the force on the current, on the force of the magnetic field, or the thrust or the motion of the conductor. And this is nothing but the magnetic field. Your index finger and your middle finger shows the direction of the induced current. FBI, or you can remember it as this is father, mother, child, and this is father, mother, induced child. How you want to remember it? Either you can use this one, father, mother, induced child, and this is father, mother, child. Left hand is father, mother, child. Right hand is father, mother, induced child. Or you can remember left hand is father, mother, child. Or you can remember this is FBI and this is father, mother, induced child. whatever is easier for you guys, please use that. But I find it easier because, like I'm a righty, so FBI, hands up. So that's what I remember it as, FBI. And this is basically father, mother, child. So you can remember it that way. Whatever floats your boat, use that, and just don't get it wrong. That's all right. Now talking about electromagnetic induction, people, like I told you before, this is what is called as EMI. So basically you need to have a moving magnetic field, only then there's a voltage induced, and because of that voltage induced, there is current flowing through the conductor. So I told you that your whole concept of transformers also works on this principle itself. Transformers also work on this very same principle. So you see this here, you have one thing called as a primary coil. This is the primary coil where you have more number of turns, and this is known as the secondary coil where you have less number of turns. So what happens is that you see that the primary coil is connected to the battery, which there is a potential difference applied, but secondary coil does not have any battery to it. All that is connected to the secondary coil is the galvanometer. There's no potential difference. But you see that as soon as you turn on the switch, there is a deflection in the secondary coil as well. Why does this happen is because this will also behave like a magnet, because it's a solenoid, so it'll have its own magnetic field. And because of the secondary coil being closer to the primary coil, the magnetic field of the primary coil gets intercepted by the secondary coil, and because of that there is a voltage induced, and because of which the galvanometer starts to deflect. So because that voltage induced, there's a current induced. But if you look at it, it doesn't last for long, because after a while, after the first couple of seconds, the magnetic field will become constant. It will become steady. It's not a changing magnetic field. It will become steady, because as soon as it becomes steady, the current in the secondary coil will also stop, or the current being induced or the voltage being induced would also basically stop. So if you talk about the factors affecting the induced current, people, there are three factors. One is the strength of the magnetic field. The stronger the magnet that I use, more would be the electromagnetic induction, or EMI. Second is the motion on the conductor. The faster I move it, the more would be the electromagnetic induction. If I move it slowly, if I move the magnet slowly, then the amount of current produced or the amount of voltage induced would be much more lesser. Then we have the length of the conductor. More is the length of the conductor, more would be the electromagnetic induction. All right. And yes, like I told you, have to use your Fleming's right hand rule in order to find out the direction of that induced current. All right, people. So yeah, that's it. That is the entire chapter. We have finished the entire chapter of magnetic effect of electric current in 35 minutes. So that's all, people. That's all. Oh, is it? Oh, is it, Sharia? Arey, nice, da. Awesome. My stories are becoming famous, no? But anyways, people, so that was the entire chapter of electromagnetic induction. If you're just joining us right now, please go through the entire, the first 30 minutes, people. I've done the entire chapter of electromagnetic, magnetic effect of electric current in this session. Whoever hasn't or who has confusions in this chapter, you'll be able to clear it up because it's a theory chapter. There is no numericals as such. It's just theory, and nothing else, right, guys? Now, let's go on to the quizzes. We'll do some quiz questions right now. Yes, there is quizzes. We'll do the quizzes right now. But before we get to the quizzes, guys, again, I would like to remind you that this is Feb already. You have 1 month left before your exams, before your exams are announced. By the end of this month, probably your exam dates would be announced. And by, by March or April, your exams would be starting. And I'm not trying to scare you people, but you need to understand the importance of this, that you have a lot of time with you right now, and how you utilize your time is what matters the most. So make the best out of it, make the best use of the time that you have right now, and make sure that you guys put in your efforts in the right direction and not get distracted. Especially right now, this is the time that you pull in all of your attention, get in all of your willpower, and start with your preparations. And I'm not just talking about physics, I'm talking about all subjects in general. You need to gather that strength within you. You need to find that strength within you to start your preparations, right, guys? So yeah, if you guys want to listen to a story, I'll tell you a small story today. Yeah, one small story about motivation. I'll give you a small motivational quote, and then we'll get into the quiz also. Since you guys have been listening for so long, let's just relax our brains a little. Our brain waves are all over the place right now, so listen carefully. So the story goes like this, guys. The story goes like this. So what happened was that there was a puddle. All right, there was a puddle, and this puddle had a lot of frogs in it. All right, lots of frogs. Now, the thing about this puddle was that right next to this puddle, there was this huge, tower. These telephone towers that you have. No, so there's this huge tower right next to the puddle. So one fine day, what happened was that one of the frogs, decided to challenge the other frogs and tell that, I am going to climb this tower and see. I want to know who's going to get to the top. So a lot of them were very, excited about this, and a lot of them, in the first few minutes itself, some of them backed out because they were like, as soon as they looked at the tower, they're like, it's too scary, I don't want to do it anymore. Some of them somehow gathered the strength and they started climbing the tower. Now, what happened was that as this competition progressed, some of them started to give up. So what happened was that there's a group of frog which was standing at the bottom who were just looked at the tower and decided not to do it. And these frogs were basically trying to scare the other frogs. They were like, it's too high, you will fall down and kill yourself. Don't do it. There's so much. It's so tall. Don't do this. Don't do that. So what happened? Majority of the frogs basically gave up halfway through. But there was this one tiny frog which did not care about all this. One tiny frog which kept on climbing, and somehow this tiny little frog managed to reach the top. And people around started wondering, because it's like this. Everyone is telling that you can't do it. But this is one tiny frog who did not care about anything and just reached the top. Now, what is the moral of the story? I'll tell you what. Apparently, guys, this tiny little frog was actually deaf. It was deaf. It could not hear. So what this tiny little frog thought was that this tiny frog thought that everyone was encouraging him. Getting it? This tiny frog thought everyone else is encouraging him. Whereas all the other frogs, just by listening to the people that they can't do it, you can't do it, they got that, even though they had the courage initially, they had that fear within them. After that, after they started telling them, after they started scaring them, they eventually gave up. But this one tiny little frog just kept on climbing. Why? Because it was deaf. And this is life, guys. This is what is life. Sometimes, in life, people will tell you you can't do it, or they'll try to bring you down. all you have to do is give a deaf ear to that. All right, because ultimately it is your life, it is your goals, it is you who's on the driving seat. Nobody else can control your life. They can tell you what to do, but whether you decide to listen to them or not, that is up to you. There'll be lots of lots of barriers in life that you face every day. And it's not, I'm not just talking about 10th standard board exam. Every day you face challenges, and that is something that life is not a bed of roses, right? Life, for every one of us, in our own ways, life is difficult. In our own ways, there are a lot of problems that for another person it might not seem like much, but at the end of the day, that is a big problem for you. But all you have to do is this: give a deaf ear, listen to yourself, and use all these things as fuel for your own motivation, for your own growth. Don't listen to them and give up on your dreams, give up on your goals. Whoever says that you can't get 90%, 80% or all, tell them to shut their mouth and keep walking. All right, because you have to, it's your life, and if you listen to them and start believing that you can't do it, then you would end up being like the other frogs. All right, people. So listen to that. All right, people. All the best. That's all I can say. Now, apart from that, people, one last thing I want to say is this, people, that the last batch of Vedantu's 9th and 10th for 10th standard at Vedantu is going to be starting on 7th of this month. This is the last batch. So if you guys are still looking for an opportunity, to start your preparations, this is the only chance that you're going to be getting, because after this it's going to be a little too late. So 7th of Feb would be the last set of batch that will be starting. So if you guys want to enroll into that batch, people, the link is given in the description of this video. So this is the last set of batch. That's it. We'll not be starting any new batches after this. And again, please make sure that you guys given a little bit more thought, because if you miss this out, then you will not have another opportunity. Then you'll be a little too late and you'll have to start your preparations elsewhere, right? Or you have to start your preparations a little later. So please don't do that to yourself. You'll be just bringing yourself down. So if you guys want to do that, the link is given in the description. You have to go to CBSE full term syllabus. Again, this is going to be the last batch. So the choice is yours. You'll be getting a flat 28% discount. That is until the end of your examinations. The price that you're going to be paying is around 5,400 rupees for all 6 subjects. Now, if you're skeptical about that, go with the 1 month program. 1 month program is 1,170. It's not 15 days. It'll be 1 month for 1,170 rupees for all 6 subjects. At least in that 1 month time, you would have started with your preparations. You would have done at least 60 to 70% of your preparations within that first month. That is by March first week. This is Feb first week. By March first week, in this 1 month, you would have at least completed 60 to 70% of your preparations of all subjects. So that is also something that you can look into. Either you go for the 15-day trial program, or if you guys want to take the full course until the end of your examinations, that would be around 5,400 rupees. So the link is right there, people. You can check it out. This will be the last set of batch. Again, I'm telling you, this will be the last batch. So you can check that out as well. With that said, people, let's go on to the quiz now. Everyone join myquiz.com. Hop into that. So you have to open up a new tab, enter joinmyquiz.com and enter the code. The game code is 941717. Let's go. Hi Nakanj, what's up? Hare Nipanji, what's up? Yes, Tenvi, what's up? Nipan, theta is nothing but the angle between magnetic field and current. Theta over there is nothing but the direction, the angle between magnetic field and current. What is the angle between magnetic field? Between magnetic field, which is B, and current I. That is what is theta over here. All right. Anyways. So when there is 2 electromagnets rather than 1 permanent and 1 electromagnet, there'll be either force of attraction or repulsion, because they are magnets at the end of the day. No, so if you have 2 electromagnets also, they will behave like a normal magnet itself. If you have 2 permanent magnets, how they would behave, this would also behave pretty much exactly the same. There'll be either force of attraction or repulsion according to that. All right. Again, over there also you have a north and south pole, right? Even if it's a electromagnet, you'll have a north and south pole. Clockwise rule. If current is going in clockwise direction, then it's south pole. Anti-clockwise, north pole. So if you bring north and north pole, it will repel. South and south pole will repel. North and south pole will have some sort of attraction. All right. All right. Not really sure, Satvika. For now, though, it is. Hi, Harsh. What's up? Hi, Muskan. What's up, Muskan? Long time no see. Windows update. Yeah. Yes, Adi. See, the thing is that even if I want to update, I can't update my Windows because apparently it's not something that I can do. I have to, get the, permission from the, the tech team and all that. So it's not up to me. Anyways, ICC results in 7th. Arey, all the best, Akanksha, all the best. Don't be nervous. Tomorrow, okay, Rishi is like tomorrow. Tomorrow's 5th, isn't it? Anyways, nonetheless, all the best, people, all the best. And don't feel nervous. I know you guys have done well. Tomorrow, the video of ICC would be coming out. So I'll be starting the quiz, people. 6 questions is what I have in store for you guys. Whoever's joining in right now, please join the quiz so that, you guys can take part in the quiz. It's joinmyquiz.com and /pro. Code is 941717. Alright, here's the first one. The magnetic field lines produced by a bar magnet originates from the South Pole and ends up in the North Pole, originates from North and ends in the East Pole, originates from North and ends in the South Pole, originates from South and ends in the West Pole. How does the magnetic field lines look around a bar magnet? Okay, everyone's done. Awesome, people. What speed? What accuracy? Let's look at the accuracy, but look at the speed. Awesome. Amisha ji, arey. Zen, congratulations. High five to you too. Fab Yash. 10 of you guys got the right answer. That is a fabulous start, people. That's a fantastic job. This is what the leaderboard looks like at this point of time. We have Zain, then we have Yash, Ayushi, Adi. When your pick will change. When is your VIP for what? When your VIP for World Cup? What? Anyways, Bhavya, Garv, Tamanna, Heritage and Nanda and NK. Congratulations, guys. Okay, moving on to the second question now. Second question on your screens. 3 seconds to prepare yourselves mentally. Here we go. It's alright, Sadvika. You can try this one. A soft iron bar is inserted inside a current carrying solenoid. The magnetic field inside the solenoid will decrease, will increase, will become zero, or will remain the same. If you enter or if you introduce a soft iron core and put it inside a solenoid, what happens to the magnetic field around it? Will it decrease, increase, will become zero, or it'll remain exactly the same? 10 seconds left. Whoever's watching it on YouTube, people, please hop into the quiz. You have to go to joinmyquiz.com/pro and enter the code. The code is 941717, if I'm not wrong. 941717. Please enter this code. Don't just sit there and watch your faces. I know that you guys admire yourself and you like looking at yourself, but right now, take part in the quiz because your exams are approaching. The more practice you get, the better you get at it. So please join the quiz. All right. 11 if you guys got the right answer. Once again, a good job, people. Absolutely correct. The strength of the magnetic field can be increased by introducing a soft iron core. So the soft iron core is basically a magnetic material. So that will also get magnetized and it will increase the magnetic field around the solenoid. Moving on to the next question, people. The next question, here we go. 3 seconds. So why not Menti? Akanksha, unfortunately, Menti and we broke up. Here's the question. An induced current is produced when a magnet is moved in a coil. The magnitude of induced current does not depend on which of these factors: the speed at which the magnet is moved, the number of turns of the coil, the resistivity of the wire of the coil, or the strength of the magnet. Which factor does it not depend on? Only that is the question. Pay attention, listen. Yes. Hi Sriram, what's up? Hi Garvji, what's up? How you doing? 3 more seconds, people. 3 more seconds. Pretty much all of you guys have already answered. 1 and your time is up. Again, people, join the quiz. Whoever's here right now, please join the quiz as well. Time's up. Looking at the leaderboard once again, we have Fab, Yash, Zain, Garv, okay, Bhavya, Garv, Tamanna and Heritage moves up a couple of spots. 10 of you guys again. That is fabulous, guys. Consistency. This is what is called as consistency. Not going up also, not going down as well. Same level you guys are maintaining. But yeah, the right answer is the resistivity of the wire because, if you talk about the induced current, it depends on the speed. It depends on the number of coils. It depends on the strength of the magnet. But what it does not depend on is the resistivity of the material. All right. It only depends on, all these other factors, but it does not depend on the resistivity of the material. Moving on to the fifth question. Fifth question. Here we go. A current flows in a wire running between S and N, that is the south and north pole of the magnet, lying horizontally as shown in the figure. So this is the figure, people. I hope you guys can see the figure. This is the figure. You have to find out the direction of the force on this conductor. Is it going to be from north to south, south to north, vertically downwards, or vertically upwards? This is the diagram. So you have to use one of the rules to find out the direction. I'm not telling you which one. You have to use one of the rules to find out the direction of the force on this conductor, on this current carrying conductor. Let's go. Hi Neelam ji, what's up? Long time no see. What's up? All right. Okay, well, quickly. Done. Awesome. Thank you, people. Here we go. This is your leaderboards once again. I don't think there's going to be much change. Oh, there is a lot of change. Bhavya goes to the top. Silent Killer. Then we have Fab. Yes, 4 of you guys got the right answer. Okay, so pay attention, guys. Pay attention. You have to use Fleming's left-hand rule for this. Current is shown by your middle finger. All right. Index finger shows the direction of the magnetic field. Magnetic field is going from left to right. All right, magnetic lines of force from left to right because north to south pole. This is the direction of magnetic field. Current is going in the upward direction. It's going this way towards the camera right now. So what is the force on this current carrying conductor? It'll be downwards. Downwards, no? Simple, da? Why is there is confusion? Why is this confusion there? Once again, people, current is shown by your middle finger. Your index finger shows the direction of the magnetic field. Magnetic field is going from north to south. This is the direction of the magnetic field. All right. Current is going in this direction. So where is your thumb pointing towards? Downwards, no? So it'll be vertically downwards. All right. That is the answer. It's okay. Happens. 4 people got it right. That is shame, puppy, shame, people. SSPS. Shame, puppy, shame. So sad. All right, next one. A student inserts a bar magnet in a coil. The student observes deflection in the galvanometer connected to the coil. What will happen if the magnet is continuously getting in and out of the coil? The current induced in the coil will increase. The current will change its direction continuously. The magnetic field will create a motion in the coil, or the magnetic field of the bar magnet would keep increasing. Let's say that he's moving it with the same velocity or the same speed. Or he's moving back and forth with the same speed. In that case, what is going to happen? The current induced in the coil will increase. The current will change the direction continuously. The magnetic field will create a motion in the conductor, or the magnetic field of the bar magnet would keep decreasing. What do you think is the right answer? Let's go, people. Let's go. Here we go. Once again, the leaderboards. This is what the leaderboard looks like. Okay. Oh my God. What is this? This full on some F1 race is going on between you guys or what? Anyways, back on the top is Fab Yash, followed by Bhavya, followed by Aishi. Then it's Tamanna, Zain, followed by Adi, Garv, Heritage, Ananya, Satvika. Hello to you, Toda. Amisha, Nanda, VIB. What's VIB? Velela Baddadari or what? And NK as well. Unfortunately, Nipun, Sam, and Ayan, it's all like no worries. But the answer to this question is option number B, guys. I'll tell you why. See, guys, if the person is moving the magnet with the same speed, then the amount of current will not change. Amount of current induced will not change. All right. Why? Because the amount of current induced will increase only if you increase the speed or the number of turns, or if you increase the strength of the magnetic field. You're not changing any of these. You're keeping all of that constant. That is why I told you, imagine that the speed is constant. In that case, the amount of current induced will be the same. But the direction would change. Why would the direction change? Because of the fact that if you use your Fleming's left-hand rule, when the direction of the force on the conductor would change, direction of the induced current will also change. The middle finger would also be showing in different direction depending on the direction of the force or the motion of the conductor. All right. So that is why the galvanometer initially goes this way, then goes this way. Why? Because when you move it closer, it might go in the other way. When you take it further away, it might go in the opposite direction. So that is the direction of the galvanometer. The needle of the galvanometer will change. That means the direction of current is changing, but the amount of current induced, that will be same as long as the speed at which you're moving the magnet remains constant. All right. That is the answer. All right, people. It's okay, happens, but yeah, guys, whatever mistakes you've made, please keep that in your mind and don't repeat those mistakes in your finals. So here is your final leaderboard. Once again, people, thanks a lot for spending your time with me. Fab Yash, fantastic job. Bhavya in the second, Ayushi in the third, Tamanna on the fourth, Zain on the fifth, Adi on the sixth, Garv on the seventh, Heritage on the eighth, Ananya on the ninth, Satvika on the 10th, 11th is Amisha, 12th is Nanda, then it's VIB and NK as well. Fabulous, guys, fabulous. So that's it from my side. That is all for today. If you have any doubts right now, you can get it cleared. If you have anything that you would like to ask me, you can ask me right now, people. Let me know. Got it? Tamanna, which diagram question? Please repeat. This one. You're talking about this one. So if you talk about this question, I'll just Okay. So if you look at the, okay, you can't see the diagram. No, you guys can see the diagram. Unfortunately, okay, wait. Let me just go back to the quiz itself. Let me uh, wait. Wait 1 second, guys. I'll just go back to the quiz again. I mean, you don't have to join the quiz and all, but you guys can see the diagram. That's why. And if I turn, okay, just take a look at the diagram for 1 second. For all those who are confused about this diagram, you take a look at the diagram. So you see this current is going in this direction. This is the direction of current. Magnetic field is going in this direction. This is the direction of magnetic field, B. All right, magnetic field is going from left to right. Current is going upwards. So what is the direction of the force on this conductor is the question. So current, I'll just show this clearly. If you look at this direction, current is going upwards, which is shown by your middle finger. All right. So magnetic field is going left to right. Current is going upwards towards the camera right now. Towards the camera, magnetic field is on left to right. So what is the force on the current carrying conductor? Downwards. All right, be downwards. That's it. All right. So that is the answer. I hope it's clear now. All right, guys, so that's it once again. And yes, thank you for joining. Thank you for spending your time with me. If you have any doubts, do let me know in the comment section. Or if you have anything, you can always reach out to me on my Instagram. Also, my Instagram handle is Anoop_Vedantu. Yes, I am on Instagram. Yes. So if you guys want to follow me, you can follow me over there as well. So it's easy question, just Flemings left hand rule. Yeah, exactly, Ari. Exactly. All right. Garv, homework quiz. Okay, I don't have any homework quizzes as such, but I can give you some homework if you want to. The homework that I would, ask you to do is basically do this. Find out. Okay, just try to find out the working principle of generators. All right, do it. I mean, try to figure out how generators work. Why? Because if you understand the working of generators, no, you'll understand the importance of the Fleming's right-hand rule. So try to do that. Try to understand how generators. I mean, it's very similar to that of a DC motor, but try to figure it out. We'll discuss that in the future sessions when we come to the Revise India part. Right? We'll discuss about that as well. But try to figure it out yourself, like the working of generators, because that'll give you a good idea of how to use Fleming's right-hand rule as well. All right, so you try to do that. All right, people. Oh, is it? Oh, sir, you told me that. Oh, yeah, definitely. Oh, okay. That, definitely, Dadi. Why not? You're still my hero. Don't worry. You're still going to be my hero in VIP4. Don't worry. Thank you, people. So that's it for today. Thank you for joining. I'll catch you guys in the next session. Have a fantastic day ahead. They basically work on induced current. No, so you try to find out the try to do that so that you will understand how to apply Fleming's right-hand rule, so that you don't have this confusions in your mind anymore. That's what I'm telling you. All right, bye, Satvika. Take care, people. Take care. If you guys like the video, hit the like button. If you guys want more such content with respect to your 10th standard preparations of all subjects, subscribe to the channel. And once again, people, the last set of batches starting from 7th of Feb. Do not miss this opportunity, a chance to start your preparations right away. If you're skeptical about spending 5,000 rupees, start with the 1 month program, which is 1,100. Again, guys, when I used to go to tuitions, when I was in 10th standard, that is in 2010, I used to pay 500 rupees per subject, right? And you're getting all 6 subjects for 1,130 rupees, which is a very good deal. So check it out. Trust me, you'll love it. Trust me, you'll be worth your time, worth your money. All right. I'll catch you guys later. Take care. Have a fantastic day ahead. See you soon. Have a nice day. See you all. Adios. Arigato. And stay safe. Sayonara. Bye, people. Take care. Thank you. Bye-bye. Peace. Peace out, people. May peace be with you. May the force be with you. Bye-bye.